Today, at exactly 3 o'clock Eastern Time, NASA will do something that's never been done before. They're going to pull back the curtain on images that shouldn't exist yet. Pictures of a cosmic traveller that came from somewhere beyond our sun's reach, captured during the one moment when everything aligned perfectly, when this visitor from another star system was at its most active, its most vulnerable, its most revealing. These aren't artist renderings. These aren't simulations. These are actual photographs taken by humanity's most powerful eyes in space, images that scientists themselves haven't fully processed yet, and in just a few hours, the world gets to see them for the first time. This is happening right now, not tomorrow, not next week, today. And what makes this moment so extraordinary isn't just that we're about to witness something unprecedented. It's that what we're about to see could rewrite what we understand about visitors from other star systems. Because the object in these images, designated 3I Atlas, is only the third confirmed interstellar object ever detected passing through our solar neighbourhood. Think about that. In all of human history, with all our telescopes and all our technology, we've only confirmed 3 objects that came from beyond our sun's gravitational family. And right now, as you're watching this, NASA is preparing to show us the most detailed look we've ever had at one of them. The Goddard Space Flight Center in Maryland is where this revelation will unfold. Scientists, researchers, and NASA leadership, including Amit Kshatriya from the Moon to Mars program, Nikki Fox, who leads NASA's Heliophysics division, and Sean Donegal-Goldman from the Goddard Astrobiology program, will be there to walk us through what we're seeing. But here's what makes this different from every other NASA announcement you've watched. These images were captured during the most critical window imaginable. They caught 3I Atlas right after it passed perihelion, that closest approach to our sun when comets transform, when their surfaces heat up and release material they've held frozen for billions of years, when they become active and revealing in ways that don't happen anywhere else in their journey. And here's the impossible part. During that exact window, the comet was positioned behind the sun from Earth's perspective. Ground-based telescopes went dark. Amateur astronomers lost their view. For weeks, this interstellar visitor performed its most dramatic act hidden from our direct sight. Yet somehow, through a coordinated effort involving multiple spacecraft positioned at different points in space, including the Hubble Space Telescope operating from its orbit above Earth's atmosphere, NASA captured it all. They watched what was supposed to be unwatchable. They photographed what should have been hidden. And today, they're sharing those images with everyone. What do you see when you capture a visitor from another star? What secrets hide in the dust that travelled through interstellar space for millions, or perhaps billions of years? What does material look like when it was formed under conditions we've never directly observed, around a star we can't identify, in a planetary system that could be anywhere in our galaxy? These aren't rhetorical questions anymore. In a few hours we start getting answers. The Hubble Space Telescope alone captured something remarkable. The sharpest pictures ever taken of 3I Atlas, showing a teardrop-shaped cloud of dust trailing from the comet's nucleus, a plume of material ejected from the sun-warmed side, patterns of activity that tell stories about what this object is made of and how it responds to our star's energy. But Hubble wasn't working alone. This was a fleet-wide effort. Multiple missions, multiple instruments, multiple perspectives, all converging on one target during its most revealing moment. Stay with me, because in the next several minutes we're going to walk through exactly why today matters. What makes this particular comet so extraordinary that NASA is treating its observation as a priority mission? What happened during those hidden weeks when it passed behind the sun? What scientists hope these images will reveal, and what this moment means for our understanding of the galaxy beyond our solar system. We're going to explore the science, the mystery, and the unprecedented nature of what's about to be unveiled. And by the time NASA's event begins at 3 o'clock Eastern, you'll understand exactly what you're looking at and why it matters. But before we go deeper, I need you to do something for me. If you're as captivated by this as I am, if the idea of seeing never-before released images of an object from another star system gives you that same sense of wonder that drew you to space exploration in the first place, hit that like button right now. Let me know this matters to you, and drop a comment telling me where you're watching from, what time it is in your part of the world, as we're all waiting together for this moment. Because that's what this is. We're part of a global audience about to witness something that happens maybe once or twice in a generation. NASA is streaming this live on NASA Plus, on their YouTube channel, Even on Amazon Prime, they want as many people as possible to experience this moment simultaneously. So let's build that community right here, right now. Tell me where you are, what brought you to this video, what you're hoping to see in those images. Let's be part of this discovery together. So why today specifically? Why is NASA making this such a significant public event instead of just releasing the images in a journal paper or a technical briefing? Understanding that answer requires understanding just how rare these moments actually are. When Oumuamua passed through our solar system back in 2017, it caught astronomers completely off guard. By the time they realized what they were looking at, an object on a trajectory that proved it came from interstellar space, it was already leaving. Scientists scrambled to observe it with whatever instruments they could point in its direction, but the window was brutally short. They got glimpses, they got data points, but they missed so much of its story because they didn't have time to prepare, didn't have the opportunity to coordinate observations across multiple platforms, couldn't capture it during its most active phases. When Tua Borisov arrived in 2019, the astronomical community had learned from that experience. They were ready, they had protocols, they knew what to look for, but even then, the observations were limited by where the comet was positioned, which telescopes had clear views, what instruments were available during its passage. It was better than Oumuamua, significantly better, but still constrained by the reality that you can't control when these visitors arrive or what path they take through our neighborhood. Now we have 3i Atlas, and everything is different. This time, NASA had months of advance warning. This time, they had the ability to coordinate their entire fleet of space-based observatories, assets that most nations don't possess, instruments positioned throughout space that can observe from angles and wavelengths impossible from Earth's surface. This time, they planned for it. The observation campaign that captured the images being released today represents an unprecedented level of coordination and coverage. They watched this comet almost continuously throughout its entire approach, perihelion passage, and beginning of its outbound journey. That's why today's event includes leadership from across NASA's science divisions. Amit Kshatriya isn't primarily a comet scientist. He oversees human exploration programs, the architecture that will take humans back to the Moon and eventually to Mars. His presence signals that NASA sees connections between understanding these interstellar visitors and understanding the broader environment humans will navigate as we become a spacefaring species. Nikki Fox leads the heliophysics division, the branch that studies our sun and its influence on the solar system. Her expertise is crucial because understanding how our star interacts with interstellar material teaches us about the boundary between our solar environment and the galaxy beyond. Sean Donegal-Goldman brings the astrobiology perspective. Questions about what these objects tell us about planetary system formation, about the distribution of chemical building blocks throughout the galaxy, about whether the materials necessary for life are common or rare among the stars. This isn't just a comet announcement. This is NASA saying that what we learn from 3i Atlas has implications across multiple fields of space science. The images being released today represent pieces of a larger puzzle about how our solar system fits into the galactic neighborhood, about what's normal and what's unique in planetary system evolution, about what other star system might have contributed to the population of objects drifting through interstellar space. And here's what makes today particularly special. NASA is making this a public event first. They're not saving these images for a conference presentation or a peer-reviewed paper. They're showing them to everyone simultaneously, creating a moment of shared discovery. You can watch on NASA Plus, their dedicated streaming platform. You can tune in on YouTube where they'll have live commentary and discussion. It's even available on Amazon Prime for people who prefer watching through their television streaming services. The agency clearly wants this to reach beyond the usual space enthusiast audience, wants to make this accessible to anyone curious about what lies beyond our solar system. The event also includes an interactive component through the hashtag AskNASA, where viewers can submit questions during the broadcast. Scientists will be available to respond to inquiries in real time, explaining what we're seeing in the images, clarifying details about the observations, discussing what surprises or confirmations the data provides. It's meant to be conversational, educational, not just a one-way presentation of findings. But underneath all that public engagement infrastructure lies the core reason today matters. These images represent our best look yet at pristine material from another star system. The Hubble observations captured details that ground-based telescopes simply cannot resolve. The sharpness of space-based imaging, free from atmospheric distortion, combined with the ability to observe in wavelengths blocked by Earth's atmosphere, means these pictures contain information that exists nowhere else. Scientists will spend months and years analyzing these images in detail, extracting data about composition, structure, behavior, and evolution. But today, we all get that first look together, that initial moment of seeing something no human eyes have ever witnessed before. Think about how rarely that happens anymore in our hyper-connected information age. Most discoveries trickle out through press releases and papers, gradually building awareness. But today there's a synchronous moment of revelation waiting for us at 3 o'clock Eastern, and that's why scientists who study these objects are treating today not as an ending but as a beginning. The beginning of understanding what this particular visitor can teach us about the galaxy beyond our sun's influence, about what's out there in the vast spaces between stars. To understand why scientists have devoted so many resources to observing this particular comet, you need to understand what makes it extraordinary, even among the rare category of interstellar visitors. Every object we've detected coming from beyond our solar system has been unique in some way, but 3i Atlas stands out in several respects that make it scientifically invaluable. First, there's the velocity. This comet is moving through our solar system at a speed that dwarfs what we typically see from objects born in our sun's gravitational family. Solar system comets, even those on highly elliptical orbits that take them to the outer reaches of the Oort cloud, are still bound to our star. Their velocities are constrained by that gravitational relationship, but 3i Atlas isn't bound to anything here. It's passing through. And the speed at which it's travelling tells us something profound about its history. That velocity wasn't generated by our sun. It's the accumulated result of millions or billions of years wandering through the galaxy, receiving gravitational nudges from every star it passed near, gaining momentum from encounters with massive objects we can't identify. By the time it reached our neighbourhood, it was carrying kinetic energy that speaks to a journey of unimaginable duration and distance. When scientists calculated its trajectory, not just where it's going, but where it came from, they found a hyperbolic orbit. That's the mathematical signature of an object that isn't captured by our sun's gravity, that will pass through our system and continue into interstellar space on the other side, never to return. Imagine the implications of that path. This comet has been travelling through the galaxy since before Earth had complex life, possibly since before our planet even formed. It has drifted past stars that no longer exist, through regions of space where new stars are still being born, across distances so vast that light itself takes thousands or tens of thousands of years to cross them. And now, for this brief window measured in months, it happens to be passing through our small corner of space, where we have the technology to observe it. But velocity alone doesn't make 3i Atlas special. Its composition raises equally intriguing questions. Early spectroscopic observations detected unusually high levels of carbon dioxide outgassing from the comet's surface. That's not unheard of in solar system comets, but the ratio compared to other volatiles is different, suggesting formation conditions that don't quite match what we see in objects from our own Oort cloud, or Kuiper belt. There are also elevated levels of nickel detected in the dust coma surrounding the nucleus, another compositional quirk that hints at formation in an environment chemically distinct from our solar system's primordial nebula. These compositional differences matter because they tell us that planetary system formation isn't identical everywhere. The star around which 3i Atlas formed, assuming it did form in a planetary system, rather than in the diffuse cloud of interstellar space itself, created conditions that produced a different recipe of materials compared to what our sun's planetary nebula produced. Different temperature gradients, different abundances of heavy elements, different timing of when volatile ices could condense onto growing bodies. Every interstellar visitor we detect expands our sample size of what's possible in planet formation, what's common across different stellar environments, and what's unique to our own solar system's history. The Hubble observations that will be highlighted in today's image release captured the comet's dust behavior in exquisite detail. That teardrop-shaped cloud trailing from the nucleus isn't random. It's the result of solar radiation pressure pushing on tiny dust particles ejected from the comet's surface as sunlight heats and vaporizes ice. The shape, density, and distribution of that dust tell scientists about the size distribution of particles leaving the surface, which in turn reveals information about the comet's structure and composition. Are we looking at fluffy, loosely bound material that breaks apart easily, or denser, more compacted structure that requires significant heating to dislodge particles? Hubble also captured what appears to be a more distinct dust tail streaming away from the Sun, separate from the broader coma. That tail represents material that's been pushed more strongly by solar radiation, particles small enough and light enough to be accelerated away from the comet, rather than just drifting in its vicinity. The presence and characteristics of that tail tell us about the dust production rate, about how actively the comet is responding to solar heating, about how different regions of the nucleus might be releasing material at different rates. What's particularly fascinating is that Hubble made these observations when 3I Atlas was already at an enormous distance from Earth. The fact that the telescope could resolve these details from so far away speaks both to Hubble's extraordinary capabilities and to how much material the comet was actively releasing. Even at great distance, even in the cold outer reaches of the solar system, this interstellar visitor was putting on a show, creating dust clouds substantial enough to be captured in sharp detail by instruments operating from Earth orbit. But here's the challenge that makes today's image release so important. Determining the actual size of 3I Atlas's nucleus has proven difficult. The nucleus itself is buried inside that dust cloud, hidden within the coma of material it's actively releasing. Scientists have to work backward from what they can see. The overall brightness, the dust distribution, the rate of material loss, to estimate what size object could produce those observations. The images being released today likely contain the data needed to refine those estimates, to better constrain how big this interstellar visitor actually is, which in turn helps calculate its mass, density, and structural characteristics. There's also the question of rotation. Comets tumble as they travel. Their rotation rates and axis orientations affect how they release material as the Sun heats different surfaces. If today's images captured enough detail over time, scientists might be able to determine rotation periods or detect asymmetries in outgassing that reveal which regions of the nucleus are more active. That information would tell us whether 3I Atlas is relatively uniform in composition, or whether it has distinct regions with different properties, perhaps a reflection of layering that occurred during its original formation billions of years ago in that unknown stellar system. Every detail matters because we're looking at a geological and chemical record from somewhere else. This isn't material from our Sun's formation. It's a sample, untouched, except by the passage of time and the occasional cosmic ray, of what existed in another planetary system when that system was young. It's a messenger from a place we can never visit, carrying information we can never obtain any other way. And that's why today's image release represents more than just pretty pictures of a comet. It's access to data about planetary formation conditions beyond our direct reach, preserved in ice and dust for eons, and now briefly available for study as this visitor passes through our cosmic neighbourhood. On October 29th, something crucial happened to 3I Atlas that scientists had been anticipating for months. The comet reached perihelion, its closest approach to our Sun during its passage through the solar system. For any comet, perihelion represents the most dramatic transformation in its entire orbit. It's the moment when solar radiation is most intense, when surface temperatures spike, when frozen volatiles buried in the nucleus suddenly vaporize and escape into space, carrying dust and larger particles with them. It's when comets become most active, most revealing, most scientifically valuable. But October 29th presented a cruel astronomical irony. Just as 3I Atlas reached this critical moment in its journey, just as it was undergoing its most significant transformation, it positioned itself almost directly behind the Sun from Earth's perspective. For ground-based observatories, the comet essentially disappeared. You can't point a telescope through the Sun. You can't observe objects positioned too close to our star's overwhelming glare. Amateur astronomers who had been tracking the comet's approach lost their target. Even professional ground-based facilities with sophisticated filters and techniques for observing near the Sun found themselves limited or completely blocked. For weeks, this interstellar visitor performed its most dramatic act hidden from direct view. The very time when scientists most wanted continuous observations, when understanding the comet's response to solar heating was most important, became a frustrating gap in ground-based coverage. If this had been a typical solar system comet, That gap wouldn't have been catastrophic. There would be other opportunities on future orbits, other perihelion passages to observe. But 3i Atlas isn't coming back. This was the only chance. Miss the perihelion passage, and that data is lost forever. This is where NASA's space-based assets proved their extraordinary value. While Earthbound telescopes went dark, instruments positioned throughout the solar system continued watching. The Stereo spacecraft, positioned away from Earth in its orbit around the Sun, had a completely different viewing angle. From Stereo's perspective, 3i Atlas wasn't hidden behind solar glare at all. The spacecraft's coronagraph instruments, designed specifically to block the Sun's direct light while observing the surrounding corona and nearby space, captured the comet's approach and perihelion passage in detail. Similarly, the LASCO C3 coronagraph, part of the Solar and Heliospheric Observatory that monitors solar activity, tracked 3i Atlas as it moved through the Sun's vicinity. These solar observing instruments weren't originally designed to study comets, but their unique positioning and filtering capabilities made them perfect for watching objects in exactly the region where ground telescopes are blind. Together, Stereo and LASCO provided continuous coverage during those critical weeks when Earth-based observations were impossible. What these spacecraft observed during perihelion was remarkable. The comet underwent rapid brightening as solar heating intensified. The dust production rate increased dramatically as more surface area vaporized and released material. The coma, that cloud of dust and gas surrounding the nucleus, expanded substantially as outgassing accelerated. These aren't just qualitative descriptions. Scientists can measure the rate of brightening, calculate dust production rates from the coma's density and extent, and determine how rapidly the comet was losing mass as it rounded the Sun. But here's what makes the timing of today's image release particularly significant. Those coronagraph observations from Stereo and LASCO captured the perihelion passage, but their resolution and wavelength coverage are limited by the instrument's primary mission of solar observation. Hubble's observations, on the other hand, were made before and after perihelion, when the comet's position allowed clear viewing from Earth orbit. By combining these different datasets, coronagraph coverage during perihelion with high-resolution Hubble, imaging before and after, scientists can reconstruct the comet's evolution through its entire closest approach phase. The images being released today likely include Hubble's post-perihelion observations when the comet was still highly active, but had moved into viewable position. That timing is ideal because the comet hadn't yet returned to the frozen dormant state it maintains in the outer solar system. It was still outgassing, still releasing material, still showing the effects of solar heating. Those post-perihelion images capture a comet in the process of transformation, revealing details about how quickly activity declines as solar heating decreases, about whether all regions of the nucleus shut down simultaneously or whether some areas remain active longer, about what the dust distribution looks like when the production rate is still elevated but declining. Scientists studying these images will be looking for specific details that address long-standing questions about comet behavior. Did the perihelion passage fracture the nucleus? Sometimes comets break apart when thermal stresses from rapid heating become too great. If 3i Atlas fragmented, the post-perihelion images would show multiple bright spots instead of a single concentrated nucleus. Did the heating expose fresh subsurface material? Comets can develop a darker, less active surface crust made of dust and non-volatile material left behind as ice sublimates. Perihelion heating can strip away that crust, exposing pristine material underneath and creating new active regions. There's also the question of asymmetric outgassing. If the comet is rotating, different parts of its surface face the Sun at different times, creating jet-like releases of material rather than uniform outgassing. Those jets carry significant force, enough in some cases to slightly alter the comet's trajectory through a rocket-like effect. Some researchers have speculated whether 3i Atlas shows evidence of non-gravitational acceleration, subtle changes in its path that don't match predictions based purely on gravitational interactions with the Sun. If such acceleration exists, today's images might reveal the asymmetric outgassing patterns responsible. What we do know with certainty is that the comet survived perihelion intact. It didn't disintegrate, it didn't fragment into multiple pieces. It emerged from that closest approach still coherent, still active, still releasing material as it began its outbound journey. That survival tells us something about its structural integrity, about whether it's a loosely bound rubble pile or a more solid body, about whether it experienced significant heating during its billions of years wandering through interstellar space before encountering our Sun. Now, as 3i Atlas continues outbound, it's gradually returning to the cold, dormant state it maintained during its interstellar journey. The window of peak activity is closing. Solar heating is decreasing as the comet recedes. Outgassing is declining. Dust production is dropping. The images captured during and immediately after perihelion represent our best opportunity to study this visitor in its most revealing state. And in just a few hours, we all get to see what that revealing moment looked like through the eyes of humanity's most capable space-based observatory. There's something almost poetic about the fact that the Hubble Space Telescope, an instrument launched before most of today's young scientists were born, remains one of our most powerful tools for studying objects at the edge of our solar system and beyond. Hubble has been operating in Earth orbit for more than 3 decades now, capturing images that have fundamentally changed our understanding of the universe. It's photographed galaxies forming in the early universe, observed planets around other stars, tracked storms on Jupiter, and mapped the distribution of dark matter through gravitational lensing. And now, in what might be one of its final major observation campaigns before eventual decommissioning, it's turned its attention to an interstellar visitor passing through our cosmic neighbourhood. The images Hubble captured of 3i Atlas represent something unprecedented in comet observation. Not because we haven't observed comets before, Hubble has studied many comets over its operational lifetime, but because we've never had the opportunity to observe an interstellar comet with this level of detail from this type of platform. When Oumuamua passed through, it was too faint and too fast for Hubble to capture useful imagery. When 2i Borisov arrived, Hubble did observe it, but the viewing geometry and timing limited what could be captured. Now, with 3i Atlas, everything aligned to provide optimal observation conditions. The sharpness Hubble achieved in these images is extraordinary when you consider the distance involved. This wasn't a nearby target. 3i Atlas was already at enormous distance from both Earth and the Sun when Hubble made these observations. Yet the telescope resolved details that ground-based observatories, even with adaptive optics systems that compensate for atmospheric distortion, simply cannot match. That's the fundamental advantage of observing from space. No atmosphere to blur the image, no weather to interrupt observations, no daytime cycles to limit viewing windows. What Hubble captured in those observations tells a complex story about the comet's activity. The teardrop-shaped dust cloud trailing from the nucleus isn't just aesthetically striking, it's a map of particle dynamics. The densest part of that teardrop, closest to the nucleus, contains the largest particles that haven't been pushed far by solar radiation pressure. As you move away from the nucleus, the dust cloud becomes more diffuse, and the particles become smaller and smaller. The shape of that gradient, the rate at which density falls off with distance, tells scientists about the size distribution of dust particles being released from the comet's surface. Scientists call this the dust size distribution, and it's crucial for understanding the comet's composition and structure. Are we looking at a body made primarily of small, fine-grained material that crumbles easily, or is there a mix of particle sizes ranging from microscopic dust to larger chunks? The Hubble images contain the data needed to answer those questions by analysing how light scatters through different parts of the coma, how the brightness distribution changes with distance from the nucleus, and how the overall structure evolves over time. Hubble also captured what appears to be a distinct plume of material ejected from the sunward side of the nucleus. This asymmetric release is exactly what you'd expect from solar heating. The side facing the sun gets hotter, ice vaporizes more rapidly, and gas pressure builds up beneath the surface until it breaks through, carrying dust with it. That plume points directly away from the sun, confirming that solar radiation is driving the activity. The width and brightness of the plume give scientists estimates of how much material is being released, how fast it's moving, and how sustained the outgassing activity is. Then there's the hint of a more extended dust tail streaming away from the sun. Tails form when solar radiation pressure and the solar wind push material away from the comet, more forcefully than the comet's own weak gravity can hold it. The smallest, lightest particles are pushed most strongly, creating that characteristic tail that always points away from the sun regardless of which direction the comet is travelling. The presence of a clearly defined tail in Hubble's images confirms that 3i Atlas was releasing enough material to create substantial dust populations that could be accelerated away by solar forces. But here's the challenge that even Hubble's extraordinary capabilities can't completely overcome. The nucleus itself remains partially hidden. It's buried inside that dust cloud, obscured by the very material it's releasing. Scientists can see the overall glow from the coma, can track how brightness is concentrated toward the center where the nucleus must be located, but they can't directly photograph the solid surface of the comet. All size estimates have to work backward from observed brightness and assumed reflectivity to calculate how large an object would need to be to produce those observations. The images being released today likely represent Hubble's best efforts to peer through that dust and constrain the nucleus size as tightly as possible. By observing at different wavelengths, by tracking how the coma evolves over time, by measuring the total amount of light being scattered by dust versus light being reflected directly from the nucleus, scientists can narrow the range of possible sizes. They can't give an exact measurement, but they can say with increasing confidence that the nucleus falls within a particular range. Those size constraints matter enormously for calculating the comet's mass, density, and ultimately its origin story. A small, dense nucleus tells a different story than a large, fluffy one. Structural properties affect how the object responds to gravitational interactions during its journey through the galaxy, how it survives close approaches to stars, and how it weathers cosmic ray bombardment over billions of years in interstellar space. Every constraint on the nucleus properties helps narrow the possibilities for where this object came from and what conditions it experienced during its formation. Hubble's observations also provide a crucial comparison point with the space-based coronagraph observations during perihelion. By looking at the comet's state before perihelion and after, scientists can measure how much activity changed during that closest solar approach. Did the comet brighten by a factor of 2, 10, more? How quickly did activity ramp up as solar heating intensified, and how quickly did it decline afterward? Those temporal evolution patterns reveal whether the comet responds rapidly to solar heating, or whether there's a lag as heat conducts into subsurface ice layers. The dust loss rate that Hubble measured is particularly interesting, because it's consistent with comets observed at similar distances from the Sun in our own solar system. That consistency suggests that whatever differences exist in 3I Atlas's composition, the basic physics of how solar heating vaporizes ice and releases dust operates the same way. It's a reminder that despite this object's exotic origin, it still obeys the same fundamental laws of physics that govern everything in our universe. The differences are in the details, in the specific chemical makeup, in the exact ratios of volatiles, in the structural characteristics that reflect formation conditions in that unknown stellar system. But the broad behavior remains comprehensible within frameworks developed from studying solar system comets. What makes today's image release so significant is that we're not just getting 1 or 2 pictures. NASA has indicated this will be a comprehensive data reveal, likely including multiple observations made at different times, perhaps even time series data showing how the comet evolved over days or weeks. That kind of dataset transforms our ability to understand dynamic processes, to see not just what the comet looked like at one moment, but how it changed, how activity waxed and waned, how the dust distribution shifted as material was released and dispersed. And that temporal dimension is where the real science happens, where models can be tested against observations, where predictions can be validated or refined. When we call 3I Atlas an interstellar object, what exactly do we mean? The term sounds exotic, almost science fiction-like, but the reality is both simpler and more profound than it might initially seem. Interstellar doesn't mean the object came from another galaxy or travelled through some kind of wormhole. It simply means it originated outside our Sun's gravitational influence, formed in another planetary system around another star, and has been wandering through the galaxy for an incomprehensibly long time before happening to cross paths with our solar system. Think about what that journey must have been like. This comet formed billions of years ago, possibly in the early days of its home planetary system, when debris from planet formation was still abundant. Maybe it was ejected by gravitational interactions with a giant planet, the same kind of process that populates our own Oort cloud with trillions of comets. But instead of settling into a stable orbit around its parent star, this one received just enough velocity to escape entirely. It left whatever stellar neighborhood birthed it and began drifting through interstellar space. For millions or billions of years, it traveled through the near vacuum between stars. The distances involved are almost impossible to conceptualize, Light itself, moving at the fastest speed physics allows, takes years to cross the space between even nearby stars. This comet, travelling at only a tiny fraction of light speed despite its remarkable velocity by solar system standards, took eons to traverse those gulfs. During that journey, it experienced essentially no external forces except the occasional gravitational nudge when it passed relatively near another star. No solar heating to sublimate its ice, no planetary encounters to alter its trajectory significantly, just cold, dark, nearly empty space. But those gravitational encounters mattered. Every time the comet passed within light years of another star, that star's gravity changed its velocity slightly, altered its trajectory incrementally. Over millions of years and countless stellar encounters, those tiny changes accumulated. The comet picked up speed with some encounters, lost speed with others, had its direction bent this way and that. By the time it reached our solar system, it carried kinetic energy that represented the integrated gravitational history of its entire galactic wandering. Astronomer David Jewett, who has studied both solar system and interstellar comets extensively, described observing these objects as like glimpsing a rifle bullet for a thousandth of a second as it passes by. You see it only for that instant when it happens to cross your field of view, moving at high speed, and then it's gone. You can't track where it came from with any precision, because by the time you notice it, it has already travelled immense distances, and projecting backward through all the gravitational influences it experienced during its journey becomes impossibly complex. That's the situation scientists face with 3I Atlas. They can precisely calculate its current trajectory. They can predict with high accuracy where it will be in the future as it leaves our solar system. But determining its origin, which stellar system birthed it, how long ago that formation occurred, what path it took through the galaxy to arrive here, those questions have no definitive answers. The uncertainties compound with every stellar encounter in its past, with every gravitational nudge that changed its velocity by some tiny amount. After millions or billions of years, the possibilities become essentially infinite. What scientists can say is that this comet represents material formed under stellar conditions different from our own suns. The star around which it originally formed might have had different metallicity, different abundances of elements heavier than hydrogen and helium. That star's planetary nebula, the disk of gas and dust from which planets and comets form, would have had different temperatures at different distances, different chemical compositions, different dynamics. All those variables affect what materials condense into solid form, what chemical compounds exist in the growing comets, what ice mixtures make up their interiors. That's why every interstellar object we detect is scientifically precious. We can study thousands of comets from our own solar system, building up detailed statistical understanding of what's normal and what's rare in our local environment. But we only have a handful of data points for what planetary formation looks like around other stars. Every interstellar visitor adds to that sample, expands our understanding of what's possible, shows us variations we didn't predict, or confirms theories we suspected were universal. The chemical anomalies in 3I Atlas, that unusual carbon dioxide abundance, those elevated nickel levels, are exactly the kinds of details that make comparative planetology possible. Are those compositions common in comets formed around other stars, or is 3I Atlas itself unusual even by interstellar standards? We won't know until we have more interstellar visitors to compare, until we build up a statistical sample large enough to identify patterns and outliers. But each object brings us incrementally closer to that understanding. There's also the profound question of population statistics. How many objects like 3I Atlas are out there? How common are interstellar wanderers passing through any given region of the galaxy at any given time? The fact that we've now detected 3 such objects in less than a decade suggests the population is substantial. But our detection capabilities are still limited. We're only finding the ones that happen to pass close enough to the sun to brighten from solar heating, that reach high enough brightness to be spotted by sky surveys, that move across our line of sight at times when we're actively looking. For every interstellar visitor we detect, how many pass through unnoticed? 10 times more? 100? 1,000? Recent models based on the detection rate of Oumuamua, 2I, Borisov and 3I Atlas suggest there might be several interstellar objects within our solar system at any given time, most too distant or too faint to observe. The galaxy, it seems, is full of these wanderers, debris from planetary system formation scattered across interstellar space over billions of years, occasionally crossing paths with other stars and their planetary families. That realization fundamentally changes how we think about our solar system's place in the galaxy. We're not isolated, not separate from the broader galactic environment. We're embedded in it, constantly receiving visitors, accumulating material from other stellar systems even as we presumably contribute our own ejected debris to the interstellar population. There's an exchange happening, slow and vast in scale, but real. And every time we detect and study one of these visitors, we're reading messages sent from places we can never directly explore, learning about conditions in stellar environments light years away, expanding our sample of how planetary systems form and evolve throughout the galaxy. That's the deeper significance of today's image release. We're not just looking at a comet, we're glimpsing the galaxy beyond our immediate neighborhood, seeing material forged under alien stellar conditions, and slowly building a comprehensive understanding of how our cosmic environment actually works. One of the most remarkable aspects of the 3i Atlas observation campaign is the coordinated nature of the effort. This wasn't just one telescope taking a few pictures. This was a comprehensive multi-platform campaign involving assets positioned throughout the solar system, operating across different wavelengths, providing complementary perspectives on a single target. And it represents a capability that, frankly, only NASA possesses at this level of sophistication. Think about what's required to pull off this kind of observation campaign. You need space-based assets positioned where they can observe without Earth's atmosphere interfering. You need instruments that can operate in different parts of the electromagnetic spectrum because different wavelengths reveal different information about composition, temperature, and structure. You need coordination between different missions, each with their own observation schedules and priorities, to ensure everyone is pointing at the same target at the right times. And you need the data processing infrastructure to combine all those observations into a coherent picture. The Hubble Space Telescope was the flagship of this campaign, capturing those high-resolution visible light images that will likely dominate today's presentation. But Hubble wasn't working in isolation. The James Webb Space Telescope, NASA's newest and most powerful observatory, also turned its infrared gaze toward 3i Atlas. Webb operates in infrared wavelengths that are completely blocked by Earth's atmosphere, but that reveal temperatures and compositions invisible to visible light telescopes. What ice mixtures exist on the comet's surface? What temperature is the nucleus? How does temperature vary across different regions as the comet rotates? Webb's infrared observations can answer those questions. The TISS spacecraft, normally focused on hunting for planets around distant stars, also participated in the observation campaign. TESS's wide-field cameras can track brightness changes over time, monitoring how the comet's overall luminosity varied as it approached perihelion, passed closest approach, and began its outbound journey. That brightness curve encodes information about activity levels, rotation rates, and surface properties. Combined with the detailed spatial imagery from Hubble, TESS's time series data helps build a complete picture of the comet's evolution. Swift Observatory brought yet another perspective with its X-ray and ultraviolet instruments. When highly energetic particles from the solar wind collide with cometary gas and dust, they can produce X-ray emission. Detecting and characterizing that emission tells scientists about the interaction between the comet's coma and the solar wind, about how material from the sun's outer atmosphere responds to encountering interstellar material. It's a different angle on the same object, revealing processes invisible to other instruments. Then there were the solar observing spacecraft, Stereoa and LASCO, that captured the perihelion passage when Earth-based and Earth-orbiting instruments couldn't observe. Those coronagraph observations filled what would have been a devastating gap in coverage, ensuring scientists didn't miss the most critical phase of the comet's journey through our solar system. The fact that NASA had assets positioned and capable of covering that observation gap demonstrates the value of maintaining a diverse fleet of spacecraft with different vantage points. Ground-based observatories also contributed, though their role was more limited during the perihelion period. The W.M. Keck Observatory in Hawaii, one of the world's most powerful ground-based telescopes, observed 3i Atlas before and after perihelion when viewing geometry allowed. Keck's spectroscopic capabilities provided detailed chemical analysis of the gases released from the comet's surface, identifying specific molecules and measuring their abundances. That spectroscopic data complements the imaging data from space-based platforms, providing chemical information that pure imagery alone cannot deliver. What makes this multi-observatory approach so powerful is that each instrument's strengths compensate for others' limitations. Hubble provides exquisite spatial resolution in visible light, but doesn't operate in infrared. Webb delivers infrared data, but at slightly lower spatial resolution. TESS tracks brightness variations over time, but doesn't provide detailed images. SWIFT reveals X-ray emission, but can't analyze chemical composition. Keck offers ground-based spectroscopy at wavelengths space telescopes might not cover. Together, these observations create a multi-dimensional dataset that captures spatial, temporal, spectral, and compositional information simultaneously. Scientists describe this as observing from multiple perspectives, and that phrasing is deliberately chosen. Just as your two eyes provide depth perception by viewing objects from slightly different angles, multiple spacecraft viewing, 3i Atlas from different positions in space provide three-dimensional information about the comet's structure and behavior. Stereo, orbiting the Sun ahead of Earth, sees the comet from a different angle than Hubble does from Earth orbit. That geometric difference allows triangulation, helps constrain distances and sizes, and reveals features that might be hidden when viewed from only one direction. The coordination required to execute this campaign is substantial. Each telescope has competing demands on its time. Hubble might need to observe distant galaxies for a cosmology program. Webb might be scheduled for exoplanet atmosphere analysis. TESS needs to maintain its planet-hunting cadence. Getting all these assets to simultaneously prioritize an interstellar comet required high-level decisions about scientific priorities, about recognizing the fleeting opportunity this object represented, about understanding that missing this observation window meant losing data forever. That's why having Amit Kshatriya from the Moon to Mars program at today's announcement is symbolically important. It signals that NASA's leadership recognizes connections across different science domains. The same infrastructure that supports space-based astronomy, communication networks, data processing systems, mission operations expertise, also supports human exploration missions. The scientific understanding we gain from studying interstellar visitors informs our knowledge of the space environment humans will navigate. There's synergy in maintaining diverse capabilities across different mission types. And here's something worth noting. This level of coordinated observation isn't just impressive as an engineering achievement, it represents a fundamentally different way of doing science compared to what was possible even 20 years ago. Previous generations of astronomers had to make do with whatever telescope they could access, whenever they could get observation time. Now, for special opportunities like 3i Atlas, there's the possibility of truly comprehensive coverage from complementary instruments working together. The data being released today represents that new paradigm: multi-wavelength, multi-platform, continuous observation of a single target through its entire passage. And the science that emerges from that kind of dataset is richer and more complete than what any single telescope could provide. So what exactly are scientists hoping to discover in the images NASA releases today? What questions might these observations answer, and what mysteries might they deepen? Understanding what researchers are looking for helps frame what we're about to see, transforms these from just pretty pictures into windows on specific scientific questions that have been waiting for answers. First and foremost, scientists want to understand the nuclear structure in as much detail as possible. Even though the nucleus itself remains partially obscured by the dust coma, the highest resolution images from Hubble should provide the best constraints yet on its size, shape, and surface properties. Is this a single coherent body? Or could it be a binary system? Two objects orbiting each other, bound by their mutual weak gravity. Binary comets exist in our solar system, formed when gravitational tidal forces during close encounters with planets pulled larger bodies apart. Could 3i Atlas have a similar structure from some encounter during its interstellar journey? The surface activity patterns are another crucial target of investigation. Not all areas of a comet's surface are equally active. Some regions might have depleted their near-surface ice, leaving behind darker, less volatile material that doesn't respond as strongly to solar heating. Other regions might have fresh ice exposed that responds dramatically when sunlight hits it. If today's images show a symmetric brightness or concentrated jets of material emanating from specific locations on the nucleus that would reveal active regions and provide information about surface heterogeneity. Scientists are also looking for evidence of rotation. Comets spin, typically with rotation periods ranging from hours to days. As the nucleus rotates, different parts of its surface face the Sun, creating periodic variations in activity and brightness. If the observation campaign captured images over a long enough time span to see brightness variations, if patterns in the dust coma shift systematically in ways that suggest different surface regions contributing at different times, researchers could determine the rotation period and axis orientation. That information reveals whether the comet is spinning rapidly or slowly, whether its rotation is stable or chaotic, whether it's tumbling end over end or spinning around a stable axis. The dust composition is another area where today's images could provide surprises. Different minerals reflect light differently, absorb or scatter at different wavelengths, and produce different colors when observed through multiple filters. If Hubble captured images at several wavelengths, blue, green, red, perhaps extending into near-infrared, analyzing the color variations throughout the dust coma reveals information about dust mineralogy. Are we seeing silicate dust similar to what solar system comets produce? Or are there compositional differences that reflect formation in a different stellar environment? There's also considerable interest in whether the observations captured any temporal evolution. Did the dust coma change shape over hours or days? Did new jets appear or existing ones shut down? Did brightness fluctuate in ways that suggest episodic outbursts of material rather than steady outgassing? Comets can be unpredictable. Sometimes subsurface ice pockets vaporize and build up pressure that eventually breaks through the surface in dramatic outbursts. Sometimes cliff faces collapse, exposing fresh material that suddenly begins outgassing. If 3I Atlas underwent any of these dynamic events during the observation period, the time series images should capture them. One particularly intriguing question that some researchers have raised involves potential non-gravitational acceleration. When comets release jets of material, those jets carry momentum. The rocket-like force of gas and dust ejecting from the surface can subtly alter the comet's trajectory in ways that pure gravitational calculations don't predict. This non-gravitational acceleration is well documented for many solar system comets. But whether it occurs for interstellar visitors, and whether it might explain some orbital peculiarities that have been discussed in the literature, remains an open question. Now, here's where I need to be careful about separating confirmed science from speculation that's circulated online. Some sources have mentioned anomalies or unexpected trajectory changes beyond what normal cometary outgassing would produce. These claims, while intriguing, haven't been confirmed in peer-reviewed scientific literature. They represent hypotheses that require careful analysis and validation. Today's images might provide data relevant to evaluating those hypotheses, by revealing the pattern and intensity of outgassing jets, by showing whether activity is symmetric or strongly asymmetric, by constraining how much momentum could plausibly be transferred to the nucleus through material ejection. But we need to approach such speculation with appropriate scientific skepticism until data confirms or rules out these possibilities. What we can say with confidence is that any unexpected findings in today's images will be taken seriously by the scientific community and subjected to rigorous analysis. If there are surprises, and there often are when observing something for the first time, researchers will propose explanations, develop models, and test predictions against additional data. That's how science advances. The images being released today become the foundation for months and years of detailed analysis, paper publications, conference presentations, and theoretical modelling. Scientists are also interested in making direct comparisons with the two previous interstellar objects. How does 3I Atlas's dust production rate compare to 2I Borisov? Is its nucleus larger or smaller? Does its composition show similar patterns or significant differences? Building up a comparative dataset across multiple interstellar visitors is how we'll eventually understand what's typical and what's unusual among these objects. What reflects universal processes versus individual formation histories? The colour of the dust and nucleus is another subtle but important detail. Is 3I Atlas reddish like many Kuiper Belt objects and some comets in our solar system? Or does it show a different colour profile that might reflect different surface processing or compositional differences? Colour in astronomical observations isn't just aesthetic, it encodes information about surface chemistry, about how material has been altered by cosmic ray bombardment during millions of years in interstellar space, about whether protective mantles of non-volatile material have built up, or whether fresh ice remains exposed. If the observations captured any spectral features, absorption or emission lines from specific molecules, those would provide direct identification of chemicals present in the coma. Water vapor, carbon dioxide, carbon monoxide, methane, ammonia. Each produces distinctive spectral signatures when observed at sufficient resolution. Hubble has spectrographic capabilities, and if those were used during the observation campaign, we might learn precisely which volatiles are outgassing and in what proportions. That chemical inventory is like a fingerprint of formation conditions in the comet's birth system. Finally, there's simply the possibility of unexpected features that no one predicted. Every time we observe something truly novel, there's a chance of seeing something that doesn't fit existing models, that challenges our assumptions, that opens new questions we hadn't thought to ask. Maybe there's an unusual structure in the dust distribution. Maybe brightness variations don't match rotation models. Maybe spectroscopic data reveals molecules that shouldn't be present or are in unexpected ratios. These surprises, when they occur, are where breakthroughs come from. That's the exciting thing about today's event. In a few hours, scientists and public alike will see these images for the first time. The researchers analysing them will undoubtedly notice details that raise new questions, that suggest follow-up observations with different instruments, that inspire theoretical work to explain unexpected findings. And we all get to be part of that moment of discovery, watching as humanity expands its understanding of what exists in the galaxy beyond our solar neighbourhood, one interstellar visitor at a time. The images being released today represent a crucial moment in our study of 3I Atlas, but they're not the end of the story. In fact, in many ways, they're the beginning, the foundation upon which months and years of additional analysis will build. And the comet itself remains observable, continues its journey through our solar system, and offers ongoing opportunities to learn more about this remarkable interstellar visitor. Right now, as 3I Atlas travels outbound from perihelion, it's gradually fading as solar heating decreases and activity declines, but it remains bright enough for continued observation through December, and potentially beyond, depending on telescope capabilities. Amateur astronomers with reasonably sized equipment can still photograph it, contributing to the ongoing dataset about how its brightness and appearance change over time. Professional observatories continue tracking it, adding to the temporal baseline of observations. In December, something particularly notable will happen. 3I Atlas will make its closest approach to Earth. Not close by any absolute standard. There's no threat, no concern about collision, but close enough that Earth-based telescopes will have their best possible viewing, geometry, their tightest resolution, their most sensitive detection of faint features. That closest approach represents another observation window that scientists are already planning for, another opportunity to capture data that complements what's being revealed today. For observers in the Northern Hemisphere, the comet is positioned in the constellation Leo during this period, near the bright star Regulus. That's a relatively easy area of sky to find, familiar to anyone who's done basic stargazing or astrophotography. The comet won't be visible to the naked eye. You'll need binoculars at minimum, and a telescope with a camera is better. But for those equipped and motivated, there's an opportunity to personally observe an object from another star system, to capture your own images of this cosmic wanderer passing through our neighbourhood. But eventually, inevitably, 3I Atlas will fade. It will continue outbound, moving farther from the Sun, receiving less and less solar heating until activity ceases entirely, and it returns to the frozen dormant state it maintained during millions of years, wandering through interstellar space. At some point, probably in early to mid-2026, it will become too faint for all but the most powerful telescopes to detect, and then it will disappear from our view entirely, a ghostly traveller returning to the darkness between stars, continuing a journey that will carry it who knows where over the next millions or billions of years. That finite observation window is exactly why today's image release matters so much. Every data point captured while 3I Atlas remains observable is a data point that will never be available again. This isn't like studying a planet in our solar system that we can return to whenever we want, that will be there for future generations with better instruments. This is a one-time opportunity. See it now, study it now, learn from it now, or miss it forever. But here's the encouraging part of this story. 3I Atlas won't be the last. The detection of 3 interstellar visitors in less than a decade tells us these objects are out there in substantial numbers. We're just beginning to develop the sky survey capabilities needed to find them. The Atlas system that discovered this comet, along with other next-generation survey programs coming online, will detect more. Not next month necessarily, not even next year, but within the coming years and decades, we'll see more interstellar visitors. Each one will add to our understanding. Each one will provide another data point for comparative studies. Each one will potentially reveal something new about planetary system formation across the galaxy. The Vera Rubin Observatory, currently in final testing before beginning full science operations, will be particularly important for this effort. Its wide-field camera and automated survey strategy are designed to find transient and moving objects, exactly the kind of capability needed to catch interstellar visitors during their brief passage through the inner solar system. When Rubin comes online, the detection rate for these objects will likely increase substantially, moving from one every few years to potentially multiple objects annually. And as our detection rate increases as we build up a statistical sample of interstellar visitors, we'll begin to see patterns emerge. We'll understand whether the compositional quirks of 3I Atlas are common or unusual. We'll discover whether most interstellar comets are similar to solar system comets, or whether there's more diversity than we currently appreciate. We'll start to constrain what planetary system formation looks like on average across the galaxy, what variations exist among different stellar environments, what's universal and what's unique to our own solar system. That's the broader context for today's image release. Yes, we're looking at one specific comet, one particular object with its own individual history and characteristics. But we're also glimpsing the beginning of a new era in astronomy, an era where studying material from other stellar systems becomes routine rather than extraordinary, where comparative planetology extends beyond our Sun's family to encompass planetary formation throughout our galactic neighbourhood. The images you're about to see at 3 o'clock Eastern aren't just pictures of a comet. They're messages from another place in the galaxy, preserved in ice and dust for eons, briefly illuminated by our Sun's warmth, captured by our most sophisticated instruments, and now decoded by scientists trying to understand what conditions exist beyond our immediate cosmic environment. They're evidence that our solar system isn't isolated, that we're constantly receiving visitors carrying information from places we can never directly explore. They're snapshots of material forged under stellar conditions different from our own, offering glimpses of what planetary formation looks like when the starting conditions vary from what our Sun provided. So when that NASA broadcast begins, when the first images appear on screen, remember that you're looking at something genuinely special, something that travelled for millions or billions of years to arrive at this moment, something that will be studied for decades to come as scientists extract every bit of information these observations contain, something that expands human knowledge about the galaxy we inhabit. And after today's event, come back here. I'll be analysing the images in detail, exploring what scientists discover in them, discussing what they reveal and what mysteries they deepen. We'll walk through this together, building understanding about what these remarkable observations tell us. But for now, it's almost time. NASA's broadcast starts at 3 o'clock Eastern. You can watch on NASA Plus, on their YouTube channel, on Amazon Prime. Choose whichever platform works best for you. Get comfortable. Maybe grab a notebook if you like taking notes during these kinds of events, and prepare to see something that no human has ever witnessed before. The closest, clearest look yet at a visitor from another star system, captured at the peak of its activity, revealed to the world in real time. This is what exploration looks like in the modern age. This is how we expand the boundaries of human knowledge, and today we all get to be part of it.